In this section, we're going to look at modeling equations. And basically, that just means we're going to be looking at how to solve word problems. Okay. Now, this is a section that usually gives students trouble. So, one of the things I suggest is looking through the process, and then we'll look at some examples. And the process, even though many people know what that process is, you really do need to think about it differently when you go to approach a word problem. Okay? So here's the process. The first thing we're going to ask you to do is read the problem. This first time you look at a word problem, you want to read it from start to finish and just get an idea of what the problem is about. Okay? The second time you read the problem, you want to pull out information. So you want to start looking for keywords, terminology like more than, less than, times, interest rates, things like that that give you a clue about the type of problem that you're looking at. Okay. Third, you want to identify your variables. Okay. This doesn't just mean I want to say, okay, I'm going to use an X here. I actually mean I want to look and know what the known quantities are and what the unknown quantities are. What is it I'm trying to find? Is there more than one thing I'm trying to find? Usually that's going to be followed by a question mark. And so that'll tell you what your variable should be. Okay. Next, I want to identify known and unknown relationships. Okay, so now that I've figured out what it is I'm trying to find, are there known quantities that relate to that variable? Are there things that I'm going to need a little bit more information about? Do I have to extrapolate something from the words that are there? Okay, and I also want to look at domains. So once I know what those unknown quantities are there variables that, or the values of the variable that don't make sense in the problem? Okay, one good example would be if I'm looking at an interest problem and I'm investing money into an account. Obviously, I can't have negative amounts of money. So if I end up with a negative answer, I know that I can throw that out. Okay. Next, you want to form your equation. And this doesn't just mean, okay, I'm going to take all the numbers and put them on some form on the paper. Forming the equation means I want to look at formulas that we know. I want to draw pictures and see if I can find relationships, like maybe a triangle and the Pythagorean theorem, or a square or a rectangle, an area, or perimeter formulas. Are there volume formulas? Are there interest formulas? Are there things like that that relate those variables so that I can put them into an equation easily? Okay. Once I have the equation, this is the part most people can do, and that's to solve the equation. So that's going to use all those concepts we talked about in the prior sections and get an answer for my variable there. Okay. And then lastly is to check your solution. And this is the step that I think most students forget to do. And it's because now that I've done all that work, I've got this answer down there. But I really need to make sure that answer not only makes sense in the problem, but it also satisfies the equation, or what it is we were asked to find. There are a lot of times with word problems, I'll get answers from students that don't quite make sense in the problem. And that's because they actually solved for something that they weren't asked to solve for. And so that means, again, when you go to check your solution, did I actually answer the problem that was asked in the situation? Okay. So let's look at an example of solving a word problem. Okay. So in this first one, Bob invested $12,000, a portion earning simple interest at 4.5% per year. The rest at 4%. After 1 year, he earned $525. How much did he invest at each rate? Okay, so we've just read the problem. We know it's now an interest problem, and we're looking for an investment. How much is being put into these different accounts? Okay, so now I'm going to reread the problem and pull out some information. Okay, so first off, we know that there was a total of $12,000. Okay, I know there was two accounts. There was a 4.5% and a 4%. Okay, and the 1 year investment was $525. Okay, so that's all I mean by rereading the problem. I'm going to go through and pull out the important information. because this right here tells me a lot. I know I have a total, which means I'm going to be adding two things together. I have some interest rates, which means I'm probably going to be looking at a simple interest problem, meaning I need a principal, the amount I put in, an interest rate, and a time. And they give me the time in there. Okay. So here, now I'm going to identify my variables. Well, I'm trying to find out how much was invested in each account. So I'm going to let X equal the amount invested at 4.5%. Okay? And then that tells me, because I have a total of 12,000, 12,000 minus X is the amount invested at 4%. Okay? So now that I know my variables, I want to also look at relationships and the domains for these. Again, X probably should not be something negative. I can't invest a negative amount of money. X probably can't be more than $12,000, because if I did, then I'm getting a negative amount for the other. So my X needs to be in the interval from 0 to 12,000. Okay? So if I get something outside of that, I know I'm not going to be getting correct values. Okay? So to form my equation, I'm going to use those relationships we talked about, which were the simple interest. It says that the interest earned at the 4.5%, which is going to be the amount I put in, times the interest rate, times the time, plus the amount at 4%, which in this case is the 12,000 minus X. This one's at 4%, and again, 1 year. Those interests earned have to total the amount of interest overall. Okay, so there's my equation. And now it's just a matter of solving that equation. Okay. So to solve, I'm going to go ahead and multiply out. So we'll get a 0.045x plus multiplying out here. Looks like a 48. We'll get 3 zeros, but I'm going to take 2 of them away, so that's 480 minus 0.04x has to equal 525. Okay, so combining like terms, notice again we're back to a linear equation, so we're going to get a 0.045 will give us a 0.5x plus 480 equal 525. We can move the 480 to the other side. So we'll get a 45 there. I'll move that over. I don't know why I wrote that so far over there. And then we just need to divide out. Okay. And so here, 45 over the 0.005. Here, to make this easy for you to divide so you don't have to use a calculator, I can move that decimal 3 points over. So I'm going to add in 3 zeros. And then 45 divided by 5 is 9 with 3 zeros. Okay. So we're going to invest $9,000 at the 4.5%. Now, again, some people will stop here, but I'm not done. I still need to find the other amount invested. Okay? And so here, remember the 12,000 minus our X is the amount at 4%. Okay? So there's our two amounts. Lastly, we want to check our solution. So first, we want to make sure these things make sense in the problem. So yes, if I add these two together, I'm going to get the total of the $12,000. And then I can check by plugging back in here to make sure that when I put in these two values, I actually get the $525. So if I take 0.045 times 9,000 plus 3,000 times 0.04, you can see that you will get the 525. Okay, so there's our solution. Okay, writing out your solutions on these does not need to be elaborate. Okay, as long as you've answered the question. So again, something like this tells me exactly what I'm looking for. How much did I invest at each rate? Well, it was $9,000, remember your units, and $3,000 here. Okay. Alright, so let's look at this next one. A painting is on a sheet of paper 20 inches wide by 15 inches high. This sheet is placed on a mat so that a uniformly wide strip of mat is showing all around the painting. If the perimeter of the mat is 102 inches, how wide should the strip of the mat be? Okay. So for this one, as I reread the problem, I'm going to actually do 2, 3, and 4 together because those things are going to relate, and in this case I'm going to need a picture to kind of see what I'm looking at. Okay. So here I've got this painting, and I know I'm going to put it on a mat so that it's a uniform strip all the way around. We know the painting itself is 20 inches by 15 inches, and the mat, uniform all the way around, just means that distance doesn't change. Okay? And then the other thing we know here is that the perimeter of this mat is 102 inches. So remember, perimeter means the distance around the outside. Okay? So that tells me if I'm looking at this length here, this is going to be 20, meaning this distance, plus x, or plus 2x. And likewise, if I'm looking at this distance, it's going to be this, the 15, plus the x, or plus 2x. Okay? So this is actually giving me my formula. Okay? X being the uniform width around the outside, so that's identifying my variable. Identifying my known and unknown relationships, well, we just did that by finding these outside dimensions, relating them to the width and the inside dimension. Domain here, well, x can't be 0 or anything less than 0, because if it's 0, there's nothing, there's no mat. And it can't be bigger than half the smallest distance. So if I look at this, if x is 7.5, that means it's going to be 7.5 this way and 7.5 this way, which covers the painting. Okay, so we don't want it to be completely covering the painting. Okay, so our domain here is going to be anything bigger than 0, but less than 15 halves. Okay. So now we can form our equation. The equation comes from the one piece of information we really haven't used in here. We've kind of used it, but we haven't really put it down. And that's this perimeter. So again, we said the perimeter is the distance around the outside. And because this is a rectangle, we know it's going to be twice this distance plus twice this distance. So our 102 inches is going to be 2 times the 20 plus 2x. Plus 2 times the 15 plus 2x. Okay. Again, at this point, we can solve our equation. So we'll distribute. Go ahead and combine like terms. From there we can move the 70 to the other side and then divide out by 8. Okay. From there, again, we're not quite done. So back to our question, we want to know how wide the strip of the mat is. So we can't just say 4. Again, we need to put our units on it. So the strip is 4 inches wide. Okay. Again, that makes sense in the problem. It's within our domain. And if we look at the picture, that kind of makes sense. It can't be more than 5 halves. And if I have 4 there and 4 there, I still have room for a picture. Likewise on the other sides. Okay. Then again, if we check inside of our equation, we can see that when we plug 4 into each of these and add those together, we will get 102 inches. In our next example, we're going to look at a mixture type problem. So here we want to know what quantity of a 60% acid solution should be mixed with a 30% acid solution to make 300 milliliters of a 50% solution. Okay. Now these problems are tricky for some people because they're just not sure how to set it up. And so here, actually a couple of the ones we're going to look at are very similar in the sense of mixture type problems. Okay. The best way to think of these is I'm going to think of the concentration of mixture 1 plus the concentration of mixture 2, and this is going to equal the total concentration. Okay, so here, going through and looking at my problems, the first mixture, I have 60% solution, but I don't know the amount, so that's going to be my variable. Okay. The second solution, I know I have 30%. I don't know the amount here, but I do know there's a total of 300 milliliters. So if I had X of them here, I know this is going to be 300 minus X. Okay. And then for the total, I know I need a 50% solution, and it's got to be a total of 300 milliliters. Okay. So think of the percentage of the mixture times the amount for each mixture, and then you can set up your total. Okay. So now I'm going to go ahead and solve. Again, if I look at my variables here, I know I can't have anything less than 0, and I can't have anything bigger than 300. So keep that in mind. My domain here, 0 to 300. From there, combining like terms, we can subtract the 90. And then divide out. Again, when you're dividing by the decimal, you can move one place over. So X will equal 200 milliliters. Okay. Again, that is within my domain. And again, it makes sense in my problem. And here, this one, unlike the last one, it didn't ask me for both solutions. It just wants to know the quantity of the 60%. So there, that's my solution. Okay. In this next example, Abe and Bob are sharing a paper route. It takes Abe 70 minutes to deliver all of the papers, and it takes Bob 80 minutes to deliver them. We want to know how long it takes both of them if they're working together. Okay. This again is almost like a mixture problem, but a little bit different. So here, because we're looking at the rate that they're working and we want to combine their rates, we have to think of the time information that we're given a little bit differently. Okay? So here, if I want to know how long it's going to take them together, I want to know the rate for Abe plus the rate for Bob, and that should give me their total rate. Okay? And once I have those rates, that's going to give me the information for the time. Okay? So this one's a little different because I'm not explicitly solving for my variable, which is time in this case. Okay? So to come up with their rates, I have to use how long it takes them to do their job. So we can think of 100% of the job being done for Abe in 70 minutes. So his rate is the whole job over the time it takes him to do it. Okay. And then if we look at Bob, again, he can do 100% of the job in 80 minutes. the total is, we don't know how long it's going to take them or what percentage of the job it's going to take them. I said that backwards. We don't know how long it's going to take them to do the whole job together. Okay. Alright, so there's our equation. What's our domain? Okay. Well, if we look at this one, first off, again, x can't be negative. We're not going to go back in time for them to finish their paper out. And it shouldn't take longer than the slowest person by themselves, right? If I take 70 minutes to do a job, if I'm working with someone else, it should take me less than that. Okay? So here, our domain is going to be 0 to 70. It should be less than 70. We don't know that it's going to be exactly half or fourth or whatever, but we know it can't be more than 70, because if it takes them longer to work together, they should just work individually. Okay? So here, to solve, well, we look at this and we've got a rational equation, so I'm going to need an LCD, which in this case looks like 560x. Okay, so I think common denominator here would be 560. We need the variable. So we'll multiply through by that common denominator. So here we'll get an 8x when multiplying by 70. We'll get a 7x when multiplying by the 80. And over here, we'll just get the 560. Okay. So adding the two together, 15x has to equal 560. X equals 560 over 15. So dividing out, we'll get a 112 over 3. It doesn't go in there evenly, but this is minutes. Okay? And if we did try to divide that out a little more, we could see this is going to be about 37.3 minutes. Okay? So it's a little more than half the time it takes Abe by himself, which seems about right. Their rates are not too different, so working together, it should be almost half the time. So there's our rate. Alright, and our last one we're going to look at is another type of mixture problem, or some people like to think of their mixture problems as distance, rate, and time problems. But either way, this is our last one. So a trip from Davenport to Omaha is 300 miles. Part of the way must be taken by bus and the rest of the way by train. The bus averages 40 miles per hour and the train 60 miles per hour. The entire trip takes 5.5 hours. We want to find out how long it takes the train. Okay, so in this case, again, we'll pull out the information we know. So we know it's a total of 300 miles. We know the bus, 40 miles per hour. Train, 60 miles per hour. And we know that the total trip, 5.5 hours. Okay. So again, we know the relationship between rates and distances is that the distance equals our rate times how long it's going to take. Okay, so there's kind of the formula we need here. Okay. So we're trying to find the time for the train ride. So we're going to let that be x. So we know 60 miles per hour, so that's our rate, times our time, plus the 40 miles per hour, that's our rate for the bus. We don't know the bus ride, and we don't know necessarily that they're the same, so we can't just use x again. But again, I know the total time. So again, I can take the 5.5 minus the x, and that's going to be their route for the bus ride. Okay. So a rate times a time, so that's a distance. A rate times the time, that's a distance. So the two distances together have to equal the total distance. Okay, so there's our equation. Domain for this, if we look, again, it's a time, so we can't have negative value there. We know our total time, so we know it can't be more than the total time. Okay. So again, we'll go ahead and simplify this equation. So just rewriting some of this, 60x, we'll go ahead and distribute here. Okay. Combine like terms. Okay, we'll go ahead and subtract off. And then divide by the 20. Okay. And again, once we get the value, we need to make sure we know what that means. So x equaling 4, this was our time it takes for the train. So this tells us the train ride is 4 hours.